Tic-tac-toe. You go first, you play your very best, and the computer never loses. Not once. How? Before every move, it looks into the future. Every move you could make, every reply it could make, all the way to the end of the game. And here is the twist. It assumes you always play your best. Then it picks the move that is safest against a perfect you. That is Minimax, the algorithm that plans ahead. One honest note before we go further. Everything here is free, no wall, no catch. This whole visual style is the idea behind my book. Algorithms and data structures, visually explained. 23 of them, each a clean diagram and runnable Python. Minimax is in there too. $24, link below. Totally optional. The full explainer is right here. Now, let us learn to plan ahead. Minimax models a game between two players who want opposite things. One player is the AI. We call it Max, because it wants the highest score. The other is the opponent. We call it Min, because it wants the lowest score. Every game state is a node. From each state, the legal moves branch out into new states. Stack those up and you get a game tree. The levels alternate. Max moves on one level, Min replies on the next, Max again below that, turn by turn, down the tree. At the very bottom sit the terminal states, the games that are already over. We score each one from Max's point of view. A win for Max is +1. A draw is 0. A loss is -1. Those leaf scores are the only hard facts we have. Everything above them, we work out. Here is the heart of it. We know the leaf scores. Now we back them up the tree, one level at a time. Look at this tree. Max is at the top. Below it are 3 Min nodes. Under each Min node are its leaves, the final scores. Start at the left Min node. Its leaves are 3, 5, and 6. Min wants the lowest, so Min takes 3. The node backs up to 3. The middle Min node has 6, 7, and 4. The lowest is 4. It backs up to 4. The right Min node has 5, 2, and 8. The lowest is 2. It backs up to 2. Now the root, which is Max chooses among 3, 4, and 2. Max wants the highest, so Max takes 4, the middle branch. That is the whole rule. At a Max node, take the maximum of the children. At a Min node, take the minimum. Alternate all the way up. The root value is 4. So the AI plays the move that leads to that 4. It has found the best move against a perfect opponent. One problem. This works perfectly on tic-tac-toe, because tic-tac-toe is tiny. Only a few thousand positions. You can search all the way to the end. Chess is not tiny. From one position there are around 30 legal moves, and games run dozens of moves deep. The full tree holds more positions than there are atoms in the universe. You cannot reach the leaves. So you stop early, at a fixed depth, say a few moves ahead. But the nodes where you stop are not finished games. They have no true score yet. So you estimate one, with a heuristic evaluation function. In chess, that function counts material and position. A queen is worth about 9, a pawn 1. Control the center, keep your king safe. It is a smart guess, not a certainty. Search deeper, and it plays better. Minimax with a good evaluation function is exactly how the classic chess engines think. There is one more trick, and it is beautiful. You can skip whole branches and still find the best move. It is called alphabeta pruning. Watch the same tree, and read it left to right. We finished the left Min node, its value is 3. So Max now has a 3 in hand. Call that alpha, the best Max has found so far. We finished the middle Min node, its value is 4. Max best is now 4. Alpha is 4. Now the right min node. Its first leaf is 5. Its second leaf is 2. Stop right there. A min node takes the lowest, so this node is worth at most 2. But max already has 4. 2 can never beat 4. Max will never come down this branch. So we do not even look at the last leaf. We prune it. The answer is identical, max still plays the 4, but we did less work. On a big tree, good pruning can roughly have the depth cost, from about O(b) to the d, toward O(b) to the d over 2. Same answer, far fewer nodes. Here it is in Python, and it is shorter than you would guess. Minimax takes a node, a remaining depth, and a flag, whose turn it is. Base case first. If the depth is 0, or the game is over, just return the evaluation of this node. No more searching below. If it is max's turn, we want the highest. Start at -infinity, loop over the children, recurse one level down with the turn flipped, and keep the maximum. If it is min's turn, we want the lowest. Start at +infinity, and keep the minimum instead. That flag, flipping on every level, is what alternates max and min down the tree. One small function, and the AI plans ahead. Let us lock it in. Minimax finds the best move by assuming the opponent plays perfectly. Build a game tree. Max levels and min levels alternate, turn by turn. Score the terminal leaves from max point of view. Then back the values up, maximum at max nodes, minimum at min nodes. The root value is the best that max can force. The AI plays the move that leads to it. Too big to finish. Stop at a depth and use a heuristic. Too slow. Prune with alphabeta. Same answer, less work. That is how a game AI plans ahead, and never loses at tic-tac-toe. So that is Minimax, the AI that looks into the future and assumes the worst from you. Behavior trees react to the world as it is right now. Minimax plans several moves ahead. Two very different kinds of game brain. But Minimax explores the same positions again and again. It is plain recursion, doing repeated work. Remember naive Fibonacci, exploding to 2 to the n. The fix is dynamic programming, solve each subproblem once, write the answer down, and reuse it. That is the next video. If you want the whole picture, 23 algorithms, each a diagram and clean Python, my book is linked below. $24, totally optional. Subscribe, and I will see you in the next one.